The first one is about Tourmaline Breccia Pipes, and the second is going to be about jadeite, and then the third one is about exploration success. So to commence with Tourmaline Breccia Pipes, this actually applies to most hydrothermal breccia pipes, but the reason I chose tourmaline pipes is because the textures are particularly well illustrated in boron-rich tourmaline pipes. What we're looking at here in the slide, it's obvious where the tourmaline pipe is. It's that black area in the landslide, and this is the Guayabanes Tourmaline Breccia pipe in southern Ecuador. An outline of the presentation, we'll talk a little bit about how Tourmaline Breccia pipes form, the typical textures that one sees, the mineralization, some examples, and then some concluding remarks. So breccias have fascinated field geologists for a very long time, including myself. My master's thesis was actually about breccia pipes, and it's a topic that I'm still very much interested in. There's quite a lot in the literature about these kinds of deposits, and I've put here a list of examples of the papers which I think are the most important that you can look at later at your leisure if you wanted to follow up on this topic. The first one is actually 1913 by a geologist whose name was Walter Weed, and he was an American geologist, very, very active field geologist, and he published some excellent papers based on field descriptions more than 100 years ago. And these were some of Weed's key observations made from a breccia pipe cluster that occurs in southeast Arizona at a place called Copper Creek. And his main comments were that there was a number of these pipes all within one area. They formed very prominent outcrops, and underground mining showed that they had an elliptical cross-section, and that the best mineralization was actually at the margin of the pipe, and it's hard for them to more or less form slivers like at some other pipes in Mexico. And he found that the contact of the breccia and the wall rock was sharp, and there was some sheeted veinings in the margins of the pipe. These observations are still very, very true today. So given this was over 100 years ago, these are excellent observations. Another very good paper followed soon after, and this was by another very prominent American geologist whose name was Emmons. He was one of the founders of the Society of Economic Geologists, actually. And in his paper, he showed a couple of things. One is that the rock on the top right shows clasts that look like they've been spalled, and then the plan view at the bottom right shows underground workings which have a elliptical shape, and they actually follow the contact of the pipe. So these were two key observations. Another paper on the same deposit came a bit later, and that showed where the mineralization was. This was an underground copper mine, and the elliptical shape is the outline of the pipe, and the brown colors are where the highest grade mineralization was. So in plan on the left and in section on the top right, we can see that the best mineralization is actually at the margin of the breccia pipe. The cut slab is one I collected at this deposit many years ago, and it shows very slab-like clasts, and I'll come to that in a minute. Chris Halls, a geologist from England, was one of the first people to publish about how these particular hydrothermal breccia pipes form. And in his paper, 1994, he shows accumulation of volatiles and fluids, boron and water at the top of a cupola, and the wall rocks eventually fracture hydraulically when the volatile pressure exceeds the lithostatic load pressure, and then we form a breccia pipe. This is the first publication I'm aware of that actually demonstrates how some of these pipes form, and it's based on the Wheel-Remfry pipe in Cornwall. I took this model and made some modifications. On the left, this is a section of a mineralized cupola and subsequent brecciation. On the left, we see the accumulations of volatiles and fluids and metals occurring at the top of the cupola. The green represents a horn-felsed carapace, which helps to prevent fluids escaping, and it builds up the pressure. In this case, the large red arrow represents major lithostatic load pressure, and the smaller arrow, VP, is the volatile pressure. If we move to the center of this cartoon, when the vapor pressure starts to exceed the lithostatic load pressure, we then fracture the wall rocks, and fluid and volatiles are released into those wall rocks. Eventually, this will form a breccia pipe, and the lithostatic load pressure and the volatile pressure will equalize, and that's the end of the formation of the breccia pipe. The scale on this is important because some of these breccia pipes have vertical extents of up to 3 kilometers. So they're pipe-like bodies with very, very long vertical extents. If we go back to the cartoon here, as we build up the volatiles and fluids on the left side of the diagram, we also are forming what's called unidirectional solidification textures. These are magmatic segregations of quartz, and the cut slab on the right shows the UST texture, and all of the black is tourmaline. So this is field evidence for overpressuring of the fluids and volatiles at the top of the cupola. The lithostatic load pressure in blue still greatly exceeds the volatile pressure in red, and as an analogy, the lid is still on the pot. The next stage is when we fracture the wall rocks hydraulically and the volatiles and fluids begin to escape into the wall rock, forming sheeted and perhaps stockwork veining, as illustrated in this cut slab. So we can see cross-cutting veins overprinting the earlier UST magmatic textures. And then finally, the volatile pressure greatly exceeds the lithostatic load pressure, and we form a proper breccia pipe. And at this point, the lid has come right off the pot. This is an example from central Mongolia, where there were multiple tourmaline breccia pipes. And in the field here on the right-hand side, what we can see are those unidirectional solidification textures. So this outcrop represents evidence for the buildup of volatiles and fluids at the top of the cupola. Then is, let me see here. Oh, sorry, yes, okay. And here's the subsequent textures from different parts in the field in that area. So on the bottom left, we have the USTs. Then we form the breccia itself, and we form shingle clasts, and then we form fluidized clasts, which show different shapes and sizes of clasts. I'll come to decompressive shock a little bit later. This particular Tourmaline Breccia pipe is the Wheel-Remfry pipe in Cornwall. It's actually formed in a very kaolinized, hydrothermally altered granite. And this was the area where Chris Halls studied his PhD, and where he conceptually came up with the formation of the breccia model. It's very well exposed, and this is quite a long time ago, but the black area represents the tourmaline pipe, and one can walk along these benches into the wall rock, to the contact of the breccia pipe, and then into the breccia. If we walk along the bench and we come towards the contact of the breccia pipe, tourmaline breccia pipes and most hydrothermal breccia pipes have very, very sharp contacts. You can literally put your hammer on the contact. And what we're looking at here is the contact of the Wheel-Remfry breccia pipe to the right of the hammer, and then the wall rocks that show sheeted fracturing on the left of the hammer. So a very nice exposure of the contact zone of a breccia pipe. And what I'd like to highlight here a little bit further on is how this breccia pipe starts to expand, and we incorporate those sheeted vein areas that we currently see in the wall rock. This too is taken from the wall rocks outside the pipe, and we see the sheeted fracturing and some hydraulic fracturing as well, where tourmaline is injected into the wall rocks. Once again, there's the nice sharp contact, and inside the pipe we have what's called shingle breccias, and these are like shingles. Perhaps the analogy is tiles, ceramic tiles on a roof. And what we're looking at here is parallel to semi-parallel orientated shingle clasts of what was previously the wall rock on the left. So the pipe contact is very obvious, but as this pipe expands, it incorporates the sheeted fracture zone that we can see on the left of the contact. The shingles that we see in the breccia were formerly vertical sheeted fractures in the wall rock. And this is described in a number of deposits by various people. Sulito and others published about this, and various other pipes around the world. And these are some more examples of shingles adjacent to sheeted fractures in wall rocks that later become shingles in the breccia. Decompressive shock is a very common texture that one sees in a tourmaline pipe and other pipes where you have severe overpressuring, remembering that this overpressuring is the fundamental cause for the formation of the pipe. Decompressive shock is a little bit like squeezing a ball with a lot of pressure, and then you suddenly and drastically drop the pressure. It quickly expands. It goes like this, and it forms these radial sheeted fracture zones around what was previously one clast. And how you can tell these textures is that essentially you can reconstruct them to one clast. However, they've undergone decompressive shock, and they form these circular to semicircular rinds around clasts. So decompressive shock is a major textural indicator for breccias that have had overpressured volatiles and fluids. And of course, that's the environment that's very favorable for mineralization and ore deposition. Some other very nice examples of decompressive shock, and these are also from Wheel Remfry, and particularly the photo on the right. It doesn't take much imagination to reconstruct all of that into one clast that later became shattered. In the central part of a pipe, the processes are entirely different. This is what we call fluidization, and this is where the volatiles and fluids are most active, and it's a little bit like putting all of these things in a washing machine and turning it up to high speed. So the fluidization process is what forms the majority of the breccia pipe, and fluidized rocks or breccias typically contain clasts of different composition. They are always rounded to sub-rounded, and they typically have a very high matrix to clast ratio. So this is another texture that can be easily recognized, and it's a diagnostic texture when interpreting breccias. This would normally take place or occur in the central part of a breccia pipe. Most hydrothermal breccia pipes are oval shaped. They're not circular. And one of the reasons for this perhaps is that the C-axis of the oval shape reflects the main structural trend within the wall rocks that the pipe is emplaced. 99% of the hydrothermal breccia pipes, and particularly tourmaline pipes that I'm aware of, all have an oval shape. Commented in a few slides earlier how breccia pipes evolved. On the left, we have a pipe that's still being formed, and as this pipe grows to the margin of the red oval shape, we start to incorporate what was formerly the sheeted veins in the wall rocks, and we end up with a larger pipe that has all these shingle clasts around the margin of the pipe, like so. The best place for mineralization in hydrothermal breccia pipes, and particularly tourmaline pipes, is always at the lobes of the C-axis. This is typical of most global examples where tourmaline breccia pipes are mineralized, and there's a reason for that. And that is because when you look at where most of the shingle clasts are, and they're at the margins that you can see here and here, is that as these pipes form, the shingles don't stack very well at the lobes of the pipes. So we have instead of having a stacking like this, we have like so, and that creates a lot of permeability for the hydrothermal fluids and volatiles. And so it's where this best permeability is that you will find the best mineralization. And of course, that has implications for exploration and how you would drill looking for mineralization in these pipes. So just to reiterate, the best permeability is always at the lobes of these breccia pipes, simply because of the way that the clasts are stacked. The middle of the pipe doesn't have as much permeability as the lobes. And of course, from a drilling perspective, if we were going to look for mineralization in tourmaline pipes, and by the way, there are a number of unexplored tourmaline pipes in the Wunto Massif that, to my knowledge, have never been drilled. They remain to be explored, and at some point in the future, these could be economic targets. So from a drilling perspective, what we don't want to do here is drill a vertical hole down the center of the pipe. We want to step outside the pipe and drill an angle through the lobe into the central part of the pipe, because that's where the mineralization should be. If we take a closer look at Los Pilares, which is in Sonora, Mexico, this incidentally was the first copper mine developed by the very famous Phelps Dodge copper mining company, which is now Freeport-McMoRan. But this was the very first copper mine that Phelps Dodge developed, and it's in Nacozari in northern Sonora. This was an underground mine. The yellow arrow indicates the very prominent outcrop of the pipe. As observed by Walter Weed, he mentioned that tourmaline pipes have prominent outcrops, and that's because they're altered and silicified, so they form nice resistant outcrops. And Pilares was an underground mine, and what they were mining in plan view was the high-grade mineralization around the margins of the pipe, and the highest grade mineralization, as we just discussed, is at the lobes of the pipes. And that was the slide I showed earlier, just to emphasize where the best mineralization is with respect to the pipe geometry, both in plan on the left and in section on the right. And here we see those nice shingle textures with mineralized matrix. There are some very nice highly mineralized tourmaline breccia pipes at what's known as the Soledad project in Peru, and I was personally involved in this project for some time. And what we found was that the best mineralization was always at the margins of the breccia pipe. These are tourmaline pipes. If we look at a profile of tourmaline breccia pipes, the upper part of the pipe will be typified by all of these nice shingle textures, and this is exactly what we see at the Soledad breccia pipes in Peru. Another example from South Korea, this is the Il Kwang mine. It was mined for copper mostly, and it was a tourmaline breccia pipe. The upper right shows that the shingles are occurring at the top and at the side of the pipe, which is exactly where would we expect them to be. And the green shades show the best grades with respect to the different levels. And once again, it's at the margins and lobes of the breccia pipe. I commented about drilling. So this is a company that was looking for mineralization in tourmaline breccia pipes in central Peru. They'd identified the breccia pipes, and some of their drill holes that you can see on the right-hand section were collared within the pipe and drilling down the pipe. What would have been much better, as shown on the left, would have been to step outside the pipe and drill through the contact and come out the other side, because that's where the best mineralization should be. Tourmaline pipes typically occur in clusters, and I've put here some examples of how many pipes that can occur within so many square kilometers. Rarely do they occur just as one pipe. And so they're actually quite difficult to explore for, because some pipes are mineralized and some aren't, but they typically occur as a cluster within several square kilometers. If we look at Soledad, which is the one I mentioned in Peru, they have 30 pipes within roughly 20 square kilometers. This is an interesting paper by Silito and Sawkins. It profiles the alteration that one sees in a vertical sense in tourmaline breccia pipes. And this is typical, actually. I've seen this now in many types. So the upper part is often characterized by quartz sericite, and then we come into the breccia pipe proper, and we have tourmaline, quartz, and sulfides. And eventually this can transition down into iron oxides and things like hematite over a vertical interval of what might be perhaps 2 kilometers. So there's the vertical alteration zoning that one can see in tourmaline breccia pipes. They have typically a very narrow diameter or small diameter compared to their vertical extent. And in the case of Sur in Chile, on the left, we see the main pipe. It has the classic alteration zoning. The diameter of the pipe is only 200 meters, but it extends for 2 kilometers. And the same applies for some other pipes, which are shown there on the other right-hand side. We talked about prominent outcrops. This is from the Soledad pipe in Peru, and the black arrow there points to a person that you can barely see, and it shows just how prominently these tourmaline pipes typically outcrop. And this can be used, these topographic features can be a good vector or a good indicator if you were flying, if you were doing an aerial survey in a prospective area. This is one I took personally from southern Mongolia. We were flying around in a small aeroplane looking for mineralization, and we came to this area, and you can see the green stained rocks. You can see that there's a lot of black rocks there, and this was thought to be a cluster of tourmaline breccia pipes, mineralized. Subsequent field work on the ground verified this, and this was quite a very interesting prospect that was subsequently drilled, but it was found from the air just by looking at residual or prominent outcrops, and in this case we could see copper staining on those outcrops. A little bit more about Soledad in detail. It's located north of Lima. It's not in the high Andes. It's at relatively modest elevation, and in this area, once again, there were prominent outcrops of multiple quartz tourmaline breccia pipes. This was originally explored for deep porphyry copper deposits. However, that was totally unsuccessful, and we can discuss that a little bit later in the presentation as to why. A classic, very prominent Tourmaline Breccia pipe is called Campanero, and this is in the Soledad field. This is yet to be drilled. It's been channel sampled, and it carries high-grade gold and copper. But this is a closer up view of one of those very prominently outcropping, highly mineralized Tourmaline Breccia pipes. The ones in the Wunto Massif also were recognized from the air as prominent outcrops. And this just shows a number of pipes in terms of the sequence of drilling. And we're going to look at mostly the Juan Carama pipe, but a lot of these pipes have now been drilled, and many of them were highly mineralized. So focusing in on Juan Carama, we can see there the drill pad and the drilling, and the H numbers represent the different pipes in this particular target area. In the drill core, there was a classic section of going from the wall rock at the top of the slide in the core tray through massive sulfide right at the breccia pipe contact into typical shingle breccias, which were highly mineralized. So exactly as we saw when we walked across the bench at Will Remfrey in Cornwall, we passed from wall rock with sheeted fractures into the contact of the pipe where the best mineralization was, and subsequently into shingle breccias. In the drill core of some of the Soledad pipes, there was fantastic evidence for decompressive shock. Remember, this was the sudden release of pressure, which created the permeability for the infilling of quartz and sulfides, and in this case, chalcopyrite, pyrite, and gold. More examples of shingles and high-grade mineralization, some spectacular copper and silver numbers with some gold, and there's some drill core photos of what some of that mineralization looked at, which occurs directly at the contact of the breccia pipes. There was one interval that was 44 meters at 7.8% copper. So these indeed can be very valid economic targets. This, a young Peruvian geologist did his PhD on this district, and this just simply shows the paragenesis of all the complex minerals that occur in the Soledad pipes. I will mention here that Tourmaline Breccia pipes can occur with two types of intrusions. One is that's directly related to a typical porphyry copper deposit, and ones that aren't related to typical porphyry copper deposits. And it's the ones that aren't related to typical porphyry copper deposits that always have this complex mineralogy. I think a final example I have here is another project that I was involved with, and that's called San Francisco de los Andes, which is located in San Juan province in Argentina. This is a view of the breccia pipes in the field. We can see that they form prominent outcrops, and the San Francisco breccia pipe had a history of previous mining. This was the exploration camp 2 years ago. For those of you that haven't worked in arid environments, this is pretty much a typical camp that one would establish for exploration. You would have a number of these tent-like dongas, summer accommodation, some would be the office, and one would be the mess and kitchen. And up on the side of the hill is the San Francisco de los Andes pipe, where the initial drilling was done. This was a historic photo of the old mine. It was previously mined for copper, bismuth, and gold almost 100 years ago. This is a plan view of the pipe. It's important here to notice two things, or three things actually. One, it has the classic oval shape. Two, the best mineralization is exactly where we predict at the lobes. And three, the small scale of the surface expression of this particular breccia pipe. It's no more than 60 kilometers long and about 30, meters, not kilometers, 60 meters in axis, C-axis, and about 20 to 30 meters across. And so at first, when you look at this, you think it's way too small. There's not going to be anything of economic significance here. However, when this was drilled, it was found that that small surface expression mushroomed out into a much larger conical shaped pipe at considerable depth. And there were some very nice intercepts at the margins of the pipe. We can see there that it's gold rich, and this mineralization was occurring at the margins of this expanding breccia pipe. This was drilled to a depth of at least 400 meters, and it was still demonstrated to be mineralized even at considerable depths. So what looked at surface to be a very small area of mineralization turned out to be a large conical shaped body that had very significant gold and copper mineralization, particularly at depth where we have 72 meters at 0.7 gold and 3.4% copper. To put this in context, an economic intercept for porphyry type environments or this situation would be anything better than a gram gold and perhaps 0.5% copper. So this particular pipe had very high grade intercepts. What does some of this mineralized material look like? Once again, classic shingles and very good evidence of decompressive shock, particularly in the bottom image of drill core, where it's very easy to construct all of those gray clasts back into one clast before it underwent decompressive shock and mineralization. Very nice circular, semicircular decompressive shock textures as well. One only sees these decompressive shock textures in non-porphyry related tourmaline pipes. Some images of the very high grade mineralization. We see the decompressive shock textures, shingles, and these of course occurring at the margins. And where is the best margin? Where is the best mineralization? Right at the margins. From the vertical section we looked at earlier, the type of alteration starts to change with depth. And what I've observed over the years is that the amount of tourmaline decreases and the amount of quartz increases with depth. And that has implications for the volumes of mineralization. And mineralization at depth in these pipes transitions from chalcopyrite basically to pyrite and quartz eventually. If we now look at some profiles of the Tourmaline Breccia pipe section, what does the bottom part of the pipe look like, as shown by that yellow bar? These are very nice outcrops of what the base of a Tourmaline Breccia pipe can look like. We don't see any shingles. We see basically it's monoclastic. We see that the matrix to class ratio is much less than higher in the pipe, and we see a lot of quartz and minor sulfide infill. So this is a nice example of what the bottom of the base of some Tourmaline Breccia pipes can look like. This is just a little higher up to the base. So what we're seeing is monoclastic clasts, very little mineralization, and a very low matrix to class ratio. That's the bottom image. If we look to the central image, we're starting to move up the pipe. We're seeing a different matrix to class ratio. And then as we come into the upper central part of the pipe, once again, the matrix to class ratio is increasing, as is the sulfide content. And we can recognize all of these levels by carefully looking at the textures. What does the top of the pipes look like? It's essentially a crackle breccia, as shown here. So there's very little matrix. In fact, it's 5% or less. And that's what we've basically done is just fractured the wall rocks above the pipe. And this is a similar thing to the sides of the upper part of the pipe. What we simply see are some sheeted fracture zones that are infilled with tourmaline and not mineralized. But this would be useful in mapping, as it would tell us we're close to the outside margin of the tourmaline pipe. A lot of people use or have been using tourmaline pipes as vectors for porphyry copper deposits. And this is just one example that I personally went to fairly recently. And the yellow zones, yellow areas shown, the breccias there, are tourmaline pipes. And a large company drilled deeper below these pipes and didn't find a porphyry. So what is a porphyry? It depends a lot at what level in the crust, the upper crust, that the intrusions are emplaced. If they're emplaced at a fairly deep level, the lithostatic load pressure prevents the porphyry or potential porphyry body to rise to an upper level in the crust where it would form typical stockwork veining and pencil type porphyries as shown on the rock slab on the right. So both of these are mineralized intrusives. The one on the left was emplaced at a much, much deeper level than the one on the right, which is a porphyry, typical porphyry copper. And that's actually from Grasberg. So it's the tourmaline pipes that form at much higher levels in the crust that are related to porphyry copper deposits. The tourmaline pipes that form at deeper levels in the crust are not typically related to classic porphyry copper deposits. This shows, and it's a very good piece of research that was done by Eric Seedorf in porphyries in the Americas. And what we're looking at here, a bar scale that shows the approximate level in the crust where the porphyry coppers form. And what we can see is that most porphyry coppers are emplaced within 3 kilometers of the paleo surface. There are exceptions that are formed much deeper in the crust, but in general, most porphyries form at shallow levels in the crust. And this is reflected in that red box. If it's 2 kilometers to 5 kilometers below the paleo surface, we have the ability to form classic porphyry copper deposits and tourmaline breccia pipes. The bottom slab is the classic V-vein porphyry copper type, and the upper image is a tourmaline breccia pipe, Los Bronces, which formed at a very shallow level in the crust. The ones that form at very shallow levels in the crust are carrot-shaped in 3D geometry. The ones that form at lower levels in the crust are cone-shaped in 3D geometry. These are the examples that form at much deeper levels in the crust. And I mentioned this is now 4 to 8 kilometers depth of emplacement. And we have the red box, which is deep level in the crust, forming cone-shaped bodies. And the yellow box forms carrot-shaped bodies, simply based on levels of emplacement in the crust. This is based mostly on my own personal observations. There's very little published about this. So some examples. This is the Saussure one I showed earlier. It's a very highly mineralized, big tourmaline breccia pipe. It's highly mineralized and it is carrot-shaped. It does not display decompressive shock textures and it does not have shingles. So they are two things that I use to distinguish the depth of emplacement and the 3D geometry of the ore body. This is another one. It's also porphyry copper related from Los Bronces in Chile, and all the mineralized tourmaline breccias are carrot-shaped. And this is what those breccias look like. Lots of tourmaline in the matrix, no decompressive shock, and no shingles. This is the Los Bronces. This is one of the bigger tourmaline breccia pipe complexes, and this is one of the largest porphyry copper deposits in the world. The typical ores from Los Bronces, specularite, from the lower levels of the tourmaline pipes, highly mineralized, no shingles, no decompressive shock. So characteristic. Same thing here in outcrop. Some drill core from the same area. Highly fluidized, characterized by the high matrix to class ratio, rounding of class of different composition, and the surface expression. Because it's carrot shaped, the top of the pipe will have a much bigger surface diameter than the pipe as we follow it down with depth. And that's the exact opposite to what we see with the intrusion-related pipes, such as San Francisco de los Andes. Drill core from Rio Blanco, exactly the same kind of looking core, Tourmaline breccias, as what we saw. Now this is Los Sulfatos. It's the same as what we saw from the previous porphyry examples. This is in Argentina, another porphyry copper district that has tourmaline pipes, very prominent outcrops. And once again, we see that the 3D geometry is carrot shaped. There's the breccias. And it's not just porphyry copper systems where one can observe this. This is from a tin-bearing tourmaline breccia pipe in Eastern Kyrgyz Republic, and we see exactly the same thing. It's been in place near surface and it's carrot shaped. And there's what the breccias look like. This is from a tungsten moly mine. Now, if we go to the non-porphyry copper examples, it's exactly the opposite in terms of the 3D geometry. And the top left shows the very prominent outcrop of the tourmaline pipe. We would have recognized that if we were flying around in a small plane or a helicopter. And it's clearly shown there on the right-hand image. This is the Washington copper moly gold silver deposit in Sonora in Mexico. The breccia is shown there in section, and it's clearly cone-shaped. What we see underground there is exactly what we'd expect. Lots of shingles and evidence for decompressive shock. So compare that and contrast that with the previous rock photos that we looked from the porphyry ones. Yet another example is from Kumababi. This is also in Mexico, in Sonora, and the breccias there are cone-shaped, and we see beautiful shingles. Here's a section that was compiled for San Francisco de los Andes that we looked at earlier. And on the left image was that very narrow surface expression that I mentioned. And then with subsequent drilling, if we understood the surface outcrops with the distribution of the mineralization, the shingle textures, the decompressive shock, we would know that with drilling, this pipe should expand and we would expect it to be cone-shaped. And that's exactly what happened when the drilling was carried out at this area. Soledad, we looked at earlier from Peru, exactly the same story. Look at the very small surface expression up there, just underneath the text that says Northwest, and then look what happened with drilling. So it really became a very substantial breccia pipe as it was drilled, and very significant mineralization at the pipe margins. So just to summarize, here's the features that can be that I've listed for non-porphyry related. They form at deeper crustal levels. They have smaller tonnages, but better grades than those with porphyries. And I mentioned earlier, they have very complex element mineralogy and signatures. They have decompressive shock. They don't have any diatremes or porphyry copper, genuine porphyry coppers associated with them. They don't transition into stockwork at depth, and they have an alteration zoning that often relates to very case bar altered intrusions at depth with weak copper. For the porphyry copper ones, it's a totally different story. They form at higher crustal levels. They have carrot shapes. They have typically only copper, moly, and gold element associations. They do indeed have associated major stockwork copper porphyry mineralization. Rarely do you see any evidence for decompressive shock textures. They have lots of porphyry vein clasts in the breccia, and they have anhydrite at depth. So these are the ones that you would drill if you were looking for a porphyry copper, a big porphyry copper deposits. And I've just summarized that in a table, just that you can look at for references later. And there's some of the examples that I've decided to use. So I'll just leave it there for a minute and I'll be back very shortly. As I commented, there's not much published about this. It's mainly my personal observations, but if we were going to look for some of these in Myanmar, particularly the Wunto Massif, where I know that some of them are, these are the kinds of guidelines that we could use to vector in for a particular style of mineralization. So by looking at the textures, particularly the element associations as well, we should be able to distinguish whether we are going to drill for a porphyry copper deposit or a higher grade, smaller polymetallic, non-porphyry related ore deposit.